Welcome to the third lecture in this year's Math Matters public lecture series that's brought to you by the Institute for Mathematics and its Applications here at the University of Minnesota. I'm Doug Arnold, the director of the IMA. I'm really delighted to be able to introduce today's speaker, who's Professor Arlie Petters, Professor of Mathematics and also Physics at Duke University. Arlie Oswald Petters grew up in a small town of Van Riga in Belize in the 1960s and 70s. He's attributed the roots of his fascination with stars to those days back in Belize when he spent nights often with very little or no electricity and could really connect directly with those stars under the Belizean sky. Petters emigrated to the United States when he was 15 years old. He double majored in math and physics in college, and then went on to MIT, where he got his PhD in mathematics in 1991. He became a faculty member at MIT for 2 years, and then he went to Princeton University, where he was on the faculty from 1993 through 1998. And then 1998 must have been a great year for Arlie. He won a prestigious Sloan Research Fellowship and a prestigious National Science Foundation Career Award. And he was recruited as the William and Sue Gross Chair of Mathematics at Duke University, where he became the first African-American scientist to hold tenure at Duke. At Duke in 2003, he was elected to their prestigious Bass Society of Fellows, and there have been many honors since. And just last month, Arlie was selected as one of two outstanding individuals by the National Academies of Science, Engineering, and Medicine to be inducted into the Portrait Gallery of African Americans in Science. Petters is the developer of the mathematical theory that seeks to explain the eerie astrophysical phenomenon that's known as gravitational lensing. Gravitational lensing comes out of the deep mathematical theory of general relativity developed by Einstein, and Einstein first posited gravitational lensing in 1915. It took about 60 years after that to actually observe gravitational lensing. In 1979, the first true observations were made. In the last 15 years, Petters has brought tremendous understanding and insight to the idea of gravitational lensing by applying deep mathematics from the fields that are known as singularity theory and Morse theory to this area. He's also pioneered ways to use gravitational lensing as a probe to understand the universe. If you're technically inclined and you want to get into it, the book to read is his big book, Singularity Theory and Gravitational Lensing, that he wrote with Levine and Blumstutz. We at the IMA, the Institute for Mathematics and its Applications, are extremely lucky that Arlie has agreed to serve on our Board of Governors, and we just began a 5-year term. And so we expect to get a lot out of him in the next 5 years, and we've started already. He's somebody who's always worked to give back to the communities he's come from, and he's recently founded a mathematics research institute in his native country of Belize. In 2002, Arlie became the first recipient of the Blackwell Tapia Prize, which is given to a mathematical scientist who's made outstanding contributions, not only to mathematics, but also to the problem of underrepresentation of minorities in mathematics. If I had to pick a single sentence to characterize Arlie Petters' career, I couldn't do better than to paraphrase some advice that he included in his acceptance speech for the Arlie Petters Award. Arlie Petters is a mathematician and a scientist who has always relentlessly pursued excellence in his work and never forgets to share freely his knowledge and experience for the benefits of those who come behind him. We're very lucky to have with us Arlie Petters, and I think we're going to have a wonderful lecture tonight.
Dr. Arnold, thank you for such a generous introduction. I must say it's such a delight to see all the young faces and the faces of various ages across the room. I will tell you today about a field that has been quite dear to my heart. And hopefully, if I can convey some of that passion, I know that many of you will walk away as gravitational lensing theorists tonight. But first, could you hear me well in the back? Excellent. Thank you. Okay, I just wanted to be sure of that. I was in Belize 2 days ago, And I realized that when I speak of gravitational lensing and the effects it's going to have in the universe, you saw in the title the word cosmic shadows. And I said, let me make sure that when I think of that, it's exactly what you're thinking of. So in Belize, we saw a lot of images like this. You see these bright lines on the edge of that boat? That's the kind of shadowing that I want you to keep in the back of your mind. In fact, you will see this kind of cobwebby type geometry show itself up when you're dealing with how gravity casts shadows in the universe. But let us begin with a little history. And as was mentioned earlier by Dr. Arnold, we have to begin with Einstein. I will define gravitational lensing quite generally as gravity's action on light. And here in this picture, you see the sun acting as the lens. It has a gravitational field that expands all the way out from it. And here you have the path of a light ray that gets curved as it passes in that gravitational field. It's an interesting problem to calculate the angle by which this light ray is bending. And you'll see how all of this will tie together with the cosmic shadows that's at the center of our story today. So what I'm going to do is take you, in a sense, on a tour and talk about some recent work that connect with this subject, the mathematical and the astrophysical aspects. So let us go back to the question of the bending angle. And here, notice that this line comes in to where you're at the closest point to the sun. And we use that to define the bending angle of the light ray. This problem was actually taken up in 1801, way before Einstein's general theory of relativity came along. It was taken up by von Soldner, and at that time, of course, it was Newton's theory of gravity that was available to analyze this problem. He had a serious concern with trying to figure out a formula for this bending angle. This was the issue. Does light have a mass? Can you treat light as a particle? Or is light a wave? And this was something that was of great concern to von Soldner, because if you treat light as a particle, you have to give it a mass. But at that time, people said light doesn't have a mass. So how do you go about doing this? As what often happens in science, you just make an assumption and see what happens. So he decided to treat this light ray as a particle flying by the sun, and he assigned a mass to it. Then used Newton's theory of gravity to try and get a formula for alpha. And I'll show you what he found. This is what it looks like. And here I have JS in honor of him. He said this formula, this tilde means approximately. He says it's twice this quantity m dot divided by r naught. And this m dot is built out of some physical quantities. For the students that have done physics in high school, this g is a gravitational constant. This capital M is the mass of the sun, and c is the speed of light. But for our purposes, this is some constant that comes out of the physics. And the r naught is the distance of closest approach that I mentioned to you that the light ray has. So he found this very simple formula that the bending angle is twice this quantity, and it goes inversely to the distance of closest approach. If you notice that formula, it has the mass of the sun in there. It doesn't have the mass of the light ray, right? So he was extremely happy that it didn't even matter that he assigned a mass to the light ray, because the answer didn't depend on it. Now, we are going to fast forward because we learned that Newton's theory isn't quite correct when you're looking at gravitational fields. And let us fast forward to Einstein in 1915. Around 1912, while Einstein was struggling with creating his general theory of relativity, if you look at some of his manuscripts, you'll see that he was testing out general relativity over and over with this problem. What is the bending angle of light? And he had no idea that von Sollner had thought about this problem in 1801. Now, in the Einsteinian point of view, he doesn't even think about assigning a mass to a light ray. And so let us take this is him in his 20s, by the way. And let's take a look at his point of view. Here's the sun, and in his perspective, gravity is not a force. It's the result of the warping of space and time. And here, this trampoline image, I'm sure many of you have seen this, represents a distortion in space. And the basic story is that massive objects deform space-time, or space in this particular picture, and light and matter move along contours of this warped geometry that's created. And here you have the Earth going around the sun. So in that point of view, he's going to calculate the bending angle. And let me show you what he found. He found that it's 4 times that quantity that von Sollner had. How you do this calculation is not particularly simple, but if you're very interested, I can tell you about it after the lecture. It's fascinating that this differs from von Sollner's answer by the factor of 2. And this is something that often happens when you're dealing with fundamental physics. There's enough of a difference between what you get using Newtonian theory and what he is getting in his brand new theory of general relativity. This you could take as the first prediction that gives you a non-trivial deviation from Newton's theory of gravity. And of course, we know that Einstein was right. I want to point out something to you that if you look at the bending angle, let me just back up a moment. Notice I said that it's approximately 4 times this quantity. So you may ask, well, that's the approximate answer. What is the full answer? And on the next slide, I'm going to show you the full answer. It turns out that this problem sat ignored for quite a long time. And for those of you who are doing calculus, you may have seen Taylor series. It turns out that you can write the answer as a Taylor series, and here it is. The first term in the Taylor series is the work that Einstein got in 1915. And here I've shown you the other terms in the series. This is some joint work that I did with Chuck Keaton at Rutgers University. And notice something interesting. It's all in that quantity m dot. This b you think of as a quantity that'll capture how close in the light rays coming. But it's a quantity that in the field we say is independent of coordinates. So it's a very important quantity to work with. Do you notice how interesting you see pi here? It's not there, and you see pi. If you keep writing out the series, you'll see it alternating like that. It's still a little bit of a mystery to me as to why that's the case. But this is the exact answer for the bending angle. Okay, so let's move on now. In 1936, I tried to find an image of Einstein when he was 56, but this was all I got. This is when he was in his 80s. In 1936, he revisited this problem. And it was at the prompting of an engineer, actually, Mandel, who said to him, well, you know, you could think of matter, the sun, as a lens that acts on light. And so one probably should look a little closer at this problem of light deflection. In other words, don't just look at the bending angle. Let's see what effects they are. And Einstein did in a 1.5-page essay. You should dig it up. It's just a 1.5 pages. And in there, he gave birth to the theory of gravitational lensing, in a sense. In this picture, you have a star acting as a deflector, and you have, here we are observing this. Now, this line I drew deliberately to show you that's the line of sight. And here's the source. What he found in the essays, if the source is off the line of sight, you're going to see 2 images of it. He didn't believe it. he said this thing can never be observed. In the same essay, he noticed that if the source is on the line of sight, so there it is, the source could be another star. It's going to appear as a very bright ring. And so now things are getting very peculiar. I can take this opportunity to introduce two pieces of terminology. This bright ring is called in scientific circles a critical curve. And this position that the source has to be in for you to get this very bright ring is called a caustic. Right? The word caustic means burning bright. And so this position is a bright spot, if you think about it, right? So putting this together, you get these two peculiar effects that he found in 1936. If the source is off the line of sight, you have double images. On the line of sight, you get this bright ring, and in a sense, you could think of the source then as being located at some bright spot in space. And this is now the new interpretation that I'm trying to give you to this essay. That if there's a bright spot, then there's likely a dark spot. And so there's a shadowing going on. To get at that, we are going to do a schematic of this. And oftentimes, to dig deeper into a particular scientific phenomenon, it's good to do a schematic and then you dig deeper and deeper and find out what's going on. So here's a schematic of the case when the source is off the line of sight. Here are the two rays that form the double images. When the source is on the line of sight, you end up having a lot of rays coming to the observer. And the end effect that you see is this critical curve or this bright ring. And the position from which you're able to get this bright ring, you get a caustic, which is just a point. And so you can summarize it as there's one bright spot, a point, and then there's the positions of these bright images that form the critical curve. Now let us go a little bit deeper, and I'll give you a fact from general relativity. In that theory, you can reverse the direction of light rays without changing the physics. And for the mathematicians in the audience, all I'm saying is that you can do an affine reparametrization of a null geodesic. So you can reverse the light rays. Here, we're reversing the light rays. And for the source that would have been off the line of sight, what it means is two rays land at this point, and that's why I have the number 2 there. If you go to the other scenario, well, it's infinitely many rays that land at that point. And so what you realize is that the bright spots are collections of a lot of light rays. And as you move off in this story, you go from infinitely many light rays to only 2. Well, then that means if you move away from that point, you're in a shadow, because there isn't going to be as much light falling there. And there it is together. This is the first shadow pattern that you could see happening due to gravitational lensing by a single star. So that is a schematic of the essay. Now here it is. If you draw the shadow pattern, you'll see that you gradually, though you have 2 images, the images are going to get dimmer. And so the white is the brightest, and as you move out, it gets dimmer. You may say, well, Arlie, wait a minute. Okay, cute. What is this good for? It seems to be a little like collecting butterflies. And I'm going to show you what it's good for. So I want you to remember that the locations of the brightest spots are called caustics. And I want you, let's look at the following question. What is the brightness profile of a source passing through the shadow pattern due to a star? So imagine this arrow is a light source, and it's moving. It enters here, passes through it, and moves out. If I'm measuring the brightness of that source, what will I see? And this is what you'll see. So remember, here I've put a circle to just give you a reference for that Einstein ring. But these are paths. Let me go back and remind you. These are paths. The horizontal lines are paths cutting across the shadow pattern. And I've put here where the caustic is located. So for this path, outside the Einstein ring, looking in the direction of the lens plane, of the light source plane, you see that this is what the brightness profile looks like. When you're at 2, notice it's climbing up. And when you're at 5, the profile has a maximum brightness. In other words, it makes sense. As you get closer to the caustic, the brightness profile peaks up, right? I still haven't told you what this is good for, but we're almost there. Well, what about this issue of detecting planets outside our solar system? Some of you may have remembered the article in the New York Times about an Earth-like planet being detected towards the direction of the center of our galaxy. I'm going to show you how you can use this to detect a planet. So here's the planet and there's a star. This is the brightness profile you get when the lens is just a star. And this is basically reinterpreting the Einstein essay. But now what if you have a star plus a planet? You'll get a little spike like that. And let me try and show you what the shadow pattern will look like. So remember that if you take, say, the sun and Earth, the sun is about 1,000,000 times more massive than the Earth. So that's a very tiny fellow next to this giant. Here's what will happen to the shadow pattern. You see, it's hard to make out. And in this scheme, the darker areas represent brighter areas. So you see, I'm going to show you a picture that draws out the caustics. So the caustics are the places from which the source will appear the brightest. It turns out when you add a planet to a star, it's no longer going to be a point. So here's the trajectory, and here's a better picture of what this looks like. This is a caustic here. It's now an entire curve. And in here, there's a little point called a cusp point. And when the source passes through here, when it's just outside that cusp point, you see that little kink? That's what you get. When it hits the first point here on that curve, this is the edge of that spike. And when it exits out the other part, that's when you get this other spike. So notice that this particular brightness profile has this very distinguished spike. It turns out that if the radius of the light source gets bigger, you're going to get a smaller spike. And this was what was in the New York Times article. This is actual data done by the Ogle team. This was just found, I think, in September last year. And it came out in the popular media. Here's a little spike. And it shows you how, by taking a very simple look at the shadow pattern, you're able to pick up the signal that tells you if there's a planet around that star that's acting as a deflector. So that is one of the first applications of this story that seems pretty cute, but you see it has a lot of depth. And I bet Einstein never imagined that today we would have been able to use that basic idea to detect extrasolar planets. Now, let's go a little bit deeper. That was just a star. Let us make the lens a little more complicated. Remember, you have interstellar dust. You're supposed to have dark matter. So let us look at the case where you have a star, uniform matter, and then there's a shear. All that means is there's surrounding matter that's tugging across the system. This is what the shadow pattern looks like. You have a very dark area. This yellowish line is the caustic curve, the brightest area, and the red indicates that you get some brightening, and the green is an area that's dimmer than the red. But inside here, there's something interesting that happens. There's no image. If you're inside here, you'll be completely invisible at any wavelength. So you imagine some futuristic war in the galaxy, and you'd see that your enemy may hide in one of these blind spots. In other words, the gravitational field can actually create blind spots in the cosmos. If you now imagine, well, what if you have several stars? You can get things that look like this. Here, these are 4 different plates, right? You have dark regions, and then you see the caustics are the yellow curves. You have bright regions, and again, the red is brighter here, the dark areas like lagoons. It's very interesting, isn't it? So, well, I'm supposed to talk about mathematics, right? And you're seeing a lot of physical things. Let us take a look at some of the mathematical issues behind this. We don't want to be too ambitious, so we'll start with a very simple problem of classifying the caustics of a typical shadow pattern due to gravity. Now, it means that it could be a star, it could be a collection of stars, it could be the entire universe. But what would be the typical shadow pattern due to a matter distribution? Here is a first step towards that answer that's in the monograph that Dr. Arnold mentioned. Caustics of a generic shadow pattern due to gravity are locally either what are called fold arcs or cusp points. You have already seen the cusp points, and the fold arcs are just the curves that connect cusp points. So the theorem is telling you that in a typical lensing situation, the brightest spots are going to look like curves or those sharp points that are cusp points. And so let me show you. So this is just the answer locally, right? If you look in a small area of the shadows. It's like trying to classify the shape of the shadows. Here is a cartoon of what is going on. If you imagine that this is a small section around that critical curve, what you could do is think of, remember how you can trace the light rays backwards? Imagine that you have this little sheet of paper, you fold it up as shown, and then you squish it down, and it comes out on this other side. The contour here would be the caustic that shows up. So this is one possibility, and that curve is called a fold curve. And the other possibility is a little area gets pleated, as shown. You squish it down, and you see the contour shape here gives you a curve with a cusp point. And so this is like a cartoon way of thinking about it. Now, over here, this is where the light source lives. This is where the light source lives. And I'm going to show you a very simple prediction that comes out of this cartoon. Imagine a light source lives here. When you look on the sky, this is the part you're going to see. This is the part you'll see. What happens if a light source sits in this shaded area next to this caustic curve? It turns out on the sky, you're going to see double images that are very close together. What happens if the source sits here interior to this cusped curve? On the sky, it predicts that you're going to see 3 images. And they're going to have this basically local form. I'm going to show you pictures that come from several observing sites of background quasars that are being affected by gravitational lenses that are entire galaxies. But first, let me set up what the caustics due to a galaxy would look like. So here you'd get an asteroid curve. So the diamond, you may remember seeing that in calculus. And here you get an ellipse. If the source sits on this fold arc, remember the theorem predicts you're going to get those double images. There might be other images far away, but remember, this is a local result. So here, the source sits here, and there are the double images. These are other images that would be floating around. If the source now goes, so here, in fact, is actual data. So let me remind you, here's the double images, and here are the other two. And this is actual data. They're the two close images. These are 4 images of the same background quasar. That was done by Paul Schechter et al. Paul is at MIT in 1997. Now let us look at it when it sits on a cusp point. You see the triplet that was predicted by the theorem, and then you have a counter image there. There's a triplet and a counter image. This is real data by the Castles group at Harvard. I think that's amazing, isn't it? Right? From these very simple analytical models, you're seeing multiple images of this type. I didn't even get into the shadows yet, right? The Einstein essay dealt with the multiple images, and then he turned over to these caustics where he saw that bright ring, right? Now, what we would then like to do, so we are able to classify the local behavior of the multiple imaging. You get these doublets or these triplets. Now, what about the geometry of the caustics in a typical shadow pattern? The best way to try and get a handle on this, and I tell you we do not even fully understand it yet, is to look at examples and look at it for more and more complex shadow patterns. So I'll show you some examples right now. Here is a shadow pattern due to a star with shear. And again, shear is where things surrounding you tug gravitationally across the star. This is what it looks like. The yellow represents the caustic, so that's the brightest area. And then the red is the next brightest, the green is the least bright. And notice outside each cusp point, you have these bright lobes. I bet you have seen this before. This is something in everyday life. You see that bright lobe? There. And if you look in your coffee cup, if you have some cream in it, you should look out for this. Right? You have the fold curve. Notice the bright areas here. And then you have the lobe of brightness. And so, as I've shown you with the opening slide, this is the kind of shadow pattern that we have some hope of understanding. We're going to look at this now in a more complicated case. We have a single star and shear. But what happens if you sprinkle a lot of small objects, like planets, around the star? What happens to this shadow pattern? Look at that. You get all these micro objects. And remember, I told you the Earth is 1,000,000 times less massive than the Sun. So it's a micro object relative to the Sun. Notice that in this picture, you don't have this curve and then you have the little one sprinkled across it. The actual arc evolves into this jagged thing. And so all these curves represent the areas where you would have the brightest spots in the shadow pattern. And I'm not even dealing with the gray areas, right? I'm just dealing with the brightest location. And so it's fascinating to see all this microstructure suddenly appear. Let us look at a little more complicated one. Here is it due to a star field. We have no shear. And notice this is the dimmest area. The yellow will be the brightest, and then the red the next brightest. But look at this shadow pattern. These simulations were done by Joachim Wamsgans, by the way, who's now, he is in Heidelberg. Doesn't this remind you of what we saw on the boat? Right? These are the caustics that are showing up on the boat. And you'll see that this type of shadow pattern becomes very important when you're dealing with certain astrophysical problems. And in particular, when you're trying to study dark matter in galactic halos. So you see there's a kind of universality in these shadow patterns on Earth and what you're getting in the cosmos. They're not drastically different, right? Here now is one due to a star field of like several 100,000 stars. And it has a shear, so you could now see the shear tugging across. If you zoom in here, this is what you see. You zoom in here, that's what you see. And here, when you get down to at its basic elements, you see the theorem that we said holding. The caustics will be either fold arcs, here's a fold arc, or cusp points. Those are the basic building blocks in this particular case, right? Even though this is a very complicated shadow pattern, as you zoom in, it's built out of fold arcs and cusp points. Here's it in color. You see the lobes showing up. Here's a very dark area. You see they can get more and more complicated. And so what we're doing is building our intuition to see examples of these shadow patterns before we take on the mathematical problem of trying to find out what it is that governs them. There it is at an even more complicated scale. It looks almost like a neural network in your brain, right? It's fascinating. So this is the problem we want to take on. And if you think about it, after you see this, you'll figure, well, how could you imagine thinking about what governs that? Only a crazy mathematician would dare take that problem on, right? Well, this is the power of mathematics, that if you want to ask yourself, and here's the problem, what mathematical law governs the global geometry of caustics in a typical shadow pattern due to gravity? That is the kind of question that mathematics can answer. It may seem almost impossible, but by abstracting the problem into a mathematical form, we can get some type of answer. I'm going to share with you some work that I did in 1995, and Doug had mentioned to you that I was fortunate to have received some recognition around those days. And this was the work that helped me with getting tenure at Duke. I have to teach you some math today, right? I can't just show you pictures. And I figured this is a type of math you probably never did before. Let us imagine you have a cusp curve that's shaped like this diamond, so it's an asteroid. And we'll orient it so that when you walk along it to the left, you're going to have two more images than what you would have on your right. Remember, you have multiple images, right? And then when I put a tilde on the curve, I'm rubbing off the cusps because they are a little too spiky for us. So this is a nice smooth curve. And then a little notation, K sub F, the F is for the word fold. That's simply like the curvature of the fold arcs, so like these things. So it's telling you how much it's bending. And now there's a formula you can use to calculate that curvature. It looks something like this, where this capital R has a name. It's called the rotation number. And then this capital N is the number of cusps on the curve. So in this formula, the only thing you don't know is what is this funny thing here. But the number of cusps, you could just count it. You see immediately a 4 on that one. And I'm going to show you how to calculate the rotation number using that curve. Let's do an example. A little simpler, you have a triangular shaped curve. Here's the formula up top. So this part of the formula we don't know how to figure out yet. And so the first thing you do is you round off the cusps, and now imagine it's a roller coaster. So what we're going to do, we're going to walk along the curve, and then we're going to go up, flip around, and come back where we started. So if from your point of view, we went counterclockwise once. Whenever that happens, the rotation number will have the value +1. Plugging it in, you get 2 pi times 1. There are 3 cusps, so you plug the 3 in there. And the formula here tells you get minus pi. Okay? Let's do the asteroid. You round off the cusps. Well, this roller coaster, let's say we start here, we ride it, but you still only make one counterclockwise loop. And so you get plus 1 again for this value. Plugging that in, you get 2 pi times 1 minus 4 pi, you get minus 2 pi as the rotation number of the fold arcs. And here's one. Now that we're experts in this stuff, let's figure that one out, right? Well, you could ride the roller coaster for it. I think you'll get dizzy. So instead, you should think of this curve as broken into different pieces. Notice this is a counterclockwise going piece. This is the same. So you have 4 counterclockwise pieces. So those will each give you plus 1. And here is a clockwise loop. That will give you minus 1. And so when you plug the answer, the net is going to be 3, 4 minus 1. And then there are 8 cusps, and you get minus 2 pi. Okay? Now, what is the mathematical law governing the geometry of these caustic curves, the bending? To do that, we have to add up these curvatures for each caustic. So I was just showing you it for one caustic. And so we'll call that capital K sub F, where we are summing it up over every caustic curve. And here's the theorem. It tells you that if the lens is smooth, so there are no black holes in that particular setting, this thing will add up to 0. And if, say, you have G stars, G could be a billion if you want, the K will add up to minus 2 pi G. I think that's amazing, right? That you can actually, from the geometry of the caustics, tell how many stars created that particular shadow pattern. This is what mathematics does. This is what geometry does, right? I'll tell you one side thing. You can actually use this formula to show that you will always have an even number of cusp points. So that muckety-muck you saw, it's governed by actual laws, mathematical laws, right? So you will never have a caustic that's shaped like a triangle. There has to be more caustics. Because if you have a single one, there'll be 3 cusps, right? And you cannot have 3 cusps. It comes right out of this formula. So let's do some examples. Here, remember you saw this when I showed you the doublet and the triplet, right? That was a model of a galaxy, a smooth model, and I've oriented the curves for you. So let's just calculate it out. You already calculated for C1, you already did that. That was minus 2 pi, remember? And here, this curve has no cusp points, and it's counterclockwise, so you get 2 pi. It adds up to 0, right? As predicted, it should add up to 0. Now let's do, you see it's consistent with the theorem. Let's do another one. Let's say you have 2 stars. The caustics, so the brightest points in the shadow pattern will look like that. You already calculated the full curvature of these individual curves. So just plug them in, you get minus 4 pi. There are 2 stars, so G is 2. If you do it in a theorem, here's a theorem, you get minus 4 pi. So it checks out. Okay? Now this was the one that gave me a heart attack. Here we have 2 stars, so G is 2. And the uniform matter, remember that the futuristic spacecraft could hide in the blind spot, right? This is what we are looking at right now. This curve is oriented clockwise, and so you know it's going to give you minus 1 in that formula. So KF is minus 2 pi. When you apply the theorem, G is 2, you get minus 4 pi. There's a problem. We have a contradiction. And I often tell my friends, I was so proud of this result, and I say, oh my goodness, it's wrong. I found a counterexample. And I looked at the proof over and over again, and I could not find a mistake. I couldn't find it, and I couldn't figure out why they're not agreeing. And I presented this issue to a colleague of mine in Germany, Hans Witt. And Hans looked at the code that was producing this. He looked at the code, and the code seemed fine. And I don't know how he did this part, but it's an example of where computer science, software and mathematics come together. He decided to look over here, and when he did that, he found that little guy sitting there right next to this arc. This line here is this, and there's a little fellow sitting right there. These two bodies, one is far less massive than the other, and creating a microcaustic, just like what I had shown you earlier. And if you zoom in on that little fellow, that's the exotic one that we saw earlier. And now recalculate it, and you're going to get out. We already calculated that. Remember, it was minus 2 pi, and you get minus 4 pi, in agreement with the theorem. Right? And this is the world of research, right? You have eureka, and you think you're a genius. And in the next breath, you're worried it's completely wrong. And that's the thrill of it. But at the end of the day, the story is the geometry, the mathematics is allowing us to penetrate these very complicated caustic patterns. And it doesn't matter how complicated the network. It is going to give you an answer that will be minus 2 pi times the number of stars involved. So the story here is that these complicated caustic patterns obey mathematical laws. And I'm not going to go much further into the story because then I'll have to get into more sophisticated mathematics, but I can at least tell you some of the current issues that are going on. On the mathematical side, classifying the caustics of the shadow pattern, we were only able to classify it locally, right? We said there you'll get cusp points or fold arcs. It's an open problem as to how to even set up a global classification. And that also connects in with the global geometry. So you want to do a global classification and then get at the global geometry. The other thing is we know that these shadow patterns are cast in space, so they are objects that are actually sheets, right? There's a three-dimensional setting that we have to look at. And everything I have been showing you, these are like two-dimensional slices through the actual shadow pattern that's created throughout the universe in space. The other thing is the stars oftentimes their positions have to be treated as random vectors. And so there's a probability aspect to it that has to be taken into account to even begin to understand the shadows. The other thing is, you realize the whole story only dealt with this part of the shadow pattern? But what about the gray areas? That is open turf. On the physical end, so these are the physical aspects, we saw an application of it to detecting extrasolar planets. But then there are other things that involve probing dark matter substructures that are supposed to be in our galaxies and in our galaxy and supposed to be moving around. You can actually use this to probe the nature of space-time around black holes. It is believed that there's a supermassive black hole at the center of our galaxy. This can be used. In other words, a black hole will create its own shadow pattern. And something that may even surprise you, you can use it to test theories of gravity. And I just completed a paper with Keaton where we use wave optics. And those of you that may remember the Young double-slit experiment, it turns out that you can use this to test brain world gravity. So for those of you who have been reading the popular literature on this, the alternative theories of gravity, brain world gravity is a descendant of the string theory idea. And you can use this to probe and test theories of that sort. So I think it's amazing how you have this very simple essay that Einstein reluctantly wrote down in 1936, come out with such a rich and deep set of structures underneath it. And as I tell you, we are just beginning to understand these cosmic shadows, right? There's an entire world ahead, and this is why I'm glad the high school students are here, because I'll be old and gray and still not fully understand this. And so I hope at the end of the day, one appreciates the power of mathematics, that you may look at something that seems insurmountable, but the power of the reasoning can lead you to discover secrets about these particular types of phenomena. I think I should stop here, right there. Thank you. Yeah.
I'm going to take a few questions in just a minute, but I thought first I would mention some of the coming attractions. The last lecture of this series will be by famous statistician and magician, Percy Diaconis, and he'll be talking about math and magic tricks on April 19th. We have just a few postcards available for this, and we'll be mailing out more. And then I wanted to mention another thing coming up. I mentioned that Arlie Petters was the first winner of the Blackwell Tapia Prize. That's named after the distinguished statistician, David Blackwell, and the distinguished mathematician, Richard Tapia. Some of you know Richard Tapia because he was a speaker in this Math Matters series a few years ago when he talked about the mathematics of drag racing. So there's a prize in the honor of David Blackwell and Richard Tapia given every 2 years, and the third one is going to be given in November. And along with that prize, there's a conference where mathematics is done, and it's also a chance for younger people and students to meet some of the great people in the field. And I'm very, very proud that we will be the host of the Blackwell Tapia Conference that will happen November 8th and 9th. I hope some people in this audience will be interested in that. And I added a mailing list. There it is. I should have had that on the other slide. But anyway, I have that email address, BT2006, Blackwell Tapia 2006, at IMA, UMN.edu. If you drop an email there, we'll make sure you stay on the mailing list and hear more about this. But now let me get back to the person you really want to hear from after that amazing lecture. I think Arlie is willing to take a couple of questions. Who gets what? Back right.
You were talking about the exclusion areas where you can't see anything. Has there been an estimate made of what percentage of the sky might actually include those? And if there is, I mean, how much that would affect our estimate of normal radiating matter in the universe that is obscured by it?
Right. The particular, you would have to have a very strong, remember it was a star embedded in continuous matter. And so you would need the continuous matter to be sufficiently dense. And I imagine things like this could probably happen around black holes that are in their early stages of development. I do not believe that these blind spots will be common, to be honest with you. I think they will be in selected regions. I mean, there will be huge regions of the sky forming behind the star. But I really don't think that there are going to be many of them. And that's kind of good too, because it would mean they're inaccessible regions even probably within our galaxy, at least from our vantage point on Earth.
What are the tests like? The last point on the slide. Right?
Oh, with the testing theories of gravity.
Yeah. Is it easy to say what the different theories predict differently about these?
That's right. Let me give you an example. When you set up, there is a way to collect a large family of gravitational theories, where general relativity will be one example. And the kinds of things that happen is, remember, take the essay with Einstein having double images. In his theory, one image is going to be brighter than the other. Now you can look at that same problem in an alternative theory of gravity, and you may see that the reverse could happen. You may see they'll spread apart more. And there are signatures that are also different at the level of the caustics. Another point I should mention is, if you wonder if there's any practical application of all of this, this is what is behind, at a very deep level, GPS technology. Because you're studying light rays propagating in the Earth's gravitational field from satellites, right? I think your cell phones have a GPS chip now. And to calculate that travel time, it's a gravitational lensing effect. Gravitational lensing also happens in time and in space. So these caustics have time delays in them. The time delay will end up being different in different theories of gravity. So you'll get to see some very distinct signatures. And let us hope that GR is totally correct, you know?
Yeah, I have a question. Can you look at something on a large scale, like say the Virgo supercluster that ran with like 10,000 or 100,000 galaxies? Can you look at that optically and then make a prediction with GL and try and compare the two and see which way things will form, say, in 10 billion years? Can you start
I've not seen any simulations that try and do future projections. But I will tell you that if you allow motion, if you allow, say, the cluster to evolve over, I don't know, a billion years, the caustics will evolve. And so there are simulations at the level of stars, and I think that could be abstracted as a first approximation to where you have bodies in a particular cluster that are evolving in time. And there's something strange that happens in the caustic network. So all that's caustics, they begin to go in a dance.
And does that give you any more information about dark matter? For
Well,
example, on the large scale, like in a supercluster.
Right. So the information that it will depend on the technology available at the time. Right? I'll give you an example. The caustics begin to dance. And I mean literally, they find partners. You see they form a partner for a moment and then split apart. And there's a dance that happens with the cusp points. And then there's some that fly across the entire network. And the question will be whether you can pick that up, for example, in a signal. I mean, that kind of thing is outside our capabilities today. And so I sort of think as to what you can access as being limited by the technology of the time. There are a lot of effects you can predict mathematically, but many of them are outside our capabilities today. So I am sure that it encodes secrets about the nature of dark matter that we don't see in some of the static images that are used today. I'm pretty sure of that.
One last question?
In the gravitational field that you said creates blind spots in the cosmos, could those blind spots be equated as being the black holes? And are the black holes then just relative to being the blind spots that you can see, that there's not necessarily a black hole, it's just relative to what's happening in the shear and in the gravitational, which creates what we're calling a black hole.
Yeah.
But there's not necessarily a black hole as just being a black hole.
Right.
Do
So
you
in
understand what I'm
terms-
saying? I don't know if I'm explaining clearly.
Yeah, I understand perfectly well. You're wondering whether the blind spots could mimic what could we confuse a blind spot with a black hole?
Yes.
And maybe are black holes really black holes? Maybe they're just blind spots. I'll say the following, that this entire story is in weak gravitational fields. And a black hole is that's perhaps one of the strongest gravitational fields you can possibly imagine. And it allows for light rays to loop around the black hole and come back out. And in fact, if you're observing a black hole that's between us, and I'm sending light rays to you, even though I'm right behind that black hole, you would still be able to see me. Because a light ray can end up wrapping around it and going to you. And so it's very hard to create a blind spot behind a black hole. It seems to want to grab everything that surrounds it and pushes it out to the observer. There is, though, the dark spot associated with a black hole. And it's the region beyond which light cannot escape. So that is something that you have to distinguish that too from the region beyond which matter cannot escape. It's a bit bigger. And when you look at the black hole in the sky, you are going to see a dark spot that is different from the blind spot that we're showing here on this right.
Oh, and if I'm hearing you correctly, that it's sounding as if there is a dark spot that you cannot really get into.
For the black
because
hole.
the light can't reflect what did you said about gravitational pull?
Yeah, so the black hole has a black spot that will always be there.
Okay.
Except that there will be no blind spot behind the black hole for you. So you'll see, so that dark spot will be where the black hole is located. However, you don't want to be near that.
Okay, on that I think we'll end tonight with Dr. Perry. On the way out.